Hello, you absolute legends. I am Eric J. Choi, and I'm going to be explaining Section 5, Explainer Video 2.1, which talks about hydraulic lifts. And jumping right in. There's a 70 kilogram student balancing a 1,200 kilogram elephant on a hydraulic lift. What is the diameter of the piston the student is standing on? And when a second student joins the first, the piston sinks 35 centimeters. So what is the second student's mass? And the diagram is right here. So first off, let's take this one step at a time and see what the problem is actually asking for. And as you can see, I highlighted the sections right here. What is the diameter of the piston that the student is standing on? And what is the second student's mass after he is added? Now, for some review before we start the problem. First off, this problem is interesting because it talks about hydraulic lifts, which is basically a clever way of using fluids in order to make a small force result in a greater force with little effort. Now note that most problems that we use a generalized formula that looks like this, because the pressure is equal on the red dotted line right here. So the atmospheric pressure on the left side, the force of the person on the left, atmospheric pressure on the right, force of the elephant on the right, and whatever water is on top of the red dotted line, we have to include that because that is hydrostatic pressure. Now you might notice that the atmospheric pressure actually cancels out, which leaves us with this equation right there. But you might notice that in the diagram right here, they're actually at the same height, so they're in equilibrium, which means there is no water difference between the two. So PGH, the hydrostatic pressure, also cancels out, which leaves us with this simple equation: F1 over A1 is equal to F2 over A2. Now note that the platforms that they're standing on are circles, so since we're looking for the radius of A1, we have to replace both A1 and A2 with their pi r squared equivalent. So pi r1 squared and pi r2 squared. Now I'll slowly scroll down, but you can see the steps in which I isolated out r1 and finally found the answer to be 0.242 meters. And note that's the radius that got shown. We have to find the diameter, so we basically just double that to 0.484. Now the problem gets a bit more trickier because the second student joins the mix and the platform sinks 35 centimeters. So we're looking for the mass of the mystery second student right here. Now, this problem will actually use this equation right here, because as you can see from the diagram, along the red dotted line, it's not the same anymore, so it's not in equilibrium. You might see that there's a water difference right here, and that is the PGH. Now, we know that the only difference between F1, between both parts A and B, is the fact that F1 now includes the mass of the mystery student. So it is equal to 70 plus ms times g. So if we convert everything regarding the forces, we get 70 plus msg over A1 is equal to 1,200 g over A2 plus 900 gh. Now, every single part of this equation has g, so it cancels out, which leaves us with this. The next step is a lot easier because all we have to do is isolate out the mass of the mystery student right here. So multiply out A1, subtract out 70, and then plug in every value that we know. And note, for A1, we solved that earlier, so it's pi r squared, but that r that we found earlier is 0.242. And if we plug in everything correctly, the mass of the mystery student should be 58.23. Thank you for watching, you absolute legends.